Hello everyone, my name is Ataullah Buriro and I'm presenting this malware detection using anomaly detection algorithms. It's actually a joint effort between three institutes, rather, Kafuskari, Foundation of Bruno Kressler and Univis. I'm thankful to all my authors for the collaboration. So now, the first question as a researcher, but before starting even that question, I would like to say here a few words about the overview of the presentation. So I'll go with some motivations and I will try to formulate the problem. What exactly is the problem? Then how the existing schemes are solving that problem and what are their limitations. We will talk about that. Then I will present our solution and at the end we will conclude with some way forwards. So the first question that I pose here, what is a malware? Malware is a code, is a software designed specifically to deceive someone, okay, to steal the data, with the motivation to steal the data or to hack the network, for example. Different malware kinds exist, like viruses, spywares, ransomwares, trojans. Everyone has different meaning and different outcome. And even from cybersecurity kiddies, script kiddies, I would say, those who just try to use different techniques, write codes, and they are optimistic to hack some network, for example, to APTs, advanced persistent attacks. These techniques are very, very popular. Now, this is the purpose of this, and motivation actually is, 450,000 malware variants are produced every day. And this study shows that like 450,000, it's really impossible to design as antivirus software that tackle all of these malware variants. So, and Google says like 2% of 14.2 million websites in the US and 11% in Italy, for example, they had malwares. So the point is, malware detection is a challenge, right? So how to detect these malwares? There exist some schemes. For example, signature-based schemes. Then we have behavior-based schemes. Then we have heuristic-based approaches, for example, model verification approaches, for example. So broadly categorize, if I broadly categorize them, there exist these 3-4 techniques. The first technique, for example, signature-based technique, fine, it works perfectly well for existing malwares. Because how it works, you see here, there are multiple known malware files exist. There are multiple bunch of data sets available. What security experts do, they just extract those signatures from these known malware files. You see here, they create the signature and they dump it somewhere in the database. Then, for every file that you download on the internet or every website that you access on the internet, for example, the signature of that particular file is matched with the existing, the computer security experts created before. If it is matched, for example, it's a virus. If it's not matched, it's not a virus. The problem here is they are fast, they are efficient for known malwares. If I know this is a malware, then it's perfectly fine. But if I don't have a signature for it, it's really difficult. So they are actually ineffective against unknown malwares. The second approach is somehow similar, but based on behavioral features. Behavioral features could be if they connect to some IP address, for example, or they are encrypting something inside. These are behaviors, So and same, if they extract those behaviors and they keep those behaviors somewhere in the database, then based on the matching of these behaviors in real time with the ones that already you did, they actually find out that okay, this is a malware or not. Okay, it can detect somehow new type of malwares as well, but their false positives are very high at the moment. Third one, heuristic. So source, analysis of code. So you need to go or write a script, for example, to review each and every line of the source code. Static analysis, we call it, or dynamic analysis. You need to create a perfect sandbox for your research. Then you have to install, and you have to run that particular file and see what happens when you run them. Also, this is effective against new type of malware, but higher false positives and they require a lot of computational resources. Last but not the least, there exist a model-based approaches as well. They're based on model verification, formal methods, for example. They also can do these this detection as well, but they have the scalability issues. It's really difficult to perform this model verification on every file. Now you saw all those 4 methods to detect malwares. Consider me as an ordinary internet user. Is it feasible for me, for example, to implement any of these security measures effectively to safeguard my identity? I need to have a perfect background for everything, if I want to do this. So what is the solution? I'm an ordinary user. I believe what I'm downloading, for example, it's all positive, so it's like anomaly detection based malware analysis. What is anomaly detection? Anomaly detection means training your model, training your machine learning classifier on only the positive data. I don't know about any category of malware, spyware, ransomware, whatever. I know only the benign data, and I want to train my model only on the benign data, and this training model, will be a very simple thing. So here you see, for example, I'm training on all the positive smileys. In negative smiley, in testing, for example, you could have positive smileys as well as the negative smileys. So the model's job will be to differentiate between them, okay, to identify this negative smiley. So actually, just to brief, these one-class classifier methods, for example, they just see the deviation between the original samples, between the samples that you are training your model on, and the testing sample, just the deviation. They are not, they don't sketch a line, for example, in case of binary class classifiers. They just see the deviation, how far this sample is, and based on this deviation, they decide whether or not this is a malware or not. They can perfectly, counter the malware threats. And higher accuracy and false positive, of course, very low, and they are very, very dynamic, and adaptive approach. How? Now, I'm presenting my motivation, our solution, how it works. Programmable executable files. I don't know if any one of you here uses Windows, but for example, 78% of the users, they are Windows. They use Windows operating system, and out of those 78% users, as in Windows, for example, all the files, if you need to install something, you need to have a programmable executable file that is called PE files, okay? And you need to, or you could run using MSI, or you can run using .dlls, for example. So idea is to, because the 78% population we have to tackle with, we are proposing something for these Windows users. And before actually starting, I would like to tell you that PE files normally, they look like this. They have multiple headers, multiple data sections, everything, okay? So here in this research, I'm going to show you how we identified these malwares from these PE headers. So without any confusion, I would say here, like there are, when we say detection, estimation, analysis, these are very confusing terms. I would say here, we have a malware file here, for example, we extracted some features, and this one, whether or not this file is a benign or is a malware, this could be done using a detection approach. This is why I'm saying this is one class classification or one class detection. Then there is a classification approach, okay? Between known and unknown malwares, and you need to separate these two categories. You could use binary class classification method, and here it will be like binary decision here, and then we have categorization method. So you have all the files, malware, spyware, ransomware, everything, and idea is to categorize those malwares. That is categorization. So we are here at IUFN. I'm presenting this one. And the approach is very simple. So you see, you are training with the green files here, and you are testing with green and red files here. You see the same features are extracted, and here you see this classification boundary that I already told you. This classifier has learned on these bunch of samples, the green ones. Here in the green one, for example, you see some red ones as well. They are false accepted. And if they are outside of this boundary, they are falsely rejected. Green ones, they are falsely rejected, and red ones, they are truly rejected. They are true negative. This is how we will report our research. And yeah. Now the data there are bunch of data sets available, and especially I'm I used for this research BODMAS dataset, which has like 134,000 samples. Okay, 77,000 are benign, others 57,000 samples are malware samples. But there exists also Umber dataset, which has more than 2 million data samples available. So it would be fun to play with those data in future. Then we have like each of, because it's a huge data, authors of these papers, for example, they have already extracted these features, but they have also created a library called a Life library. You could use also that library to extract those features by yourself if you want. Or if you want to combine those Life features with some features extracted from Yara rules or extracted from some static analysis, you can do it by your own if you want. So we created these data sets, we extracted these features, and we created also the feature vector of these observation. Each observation is represented by 2, 3, 8, 1 features. So the feature space is very high dimensional. And what we did, for example, we have from the benign data set comprising of all these features, we have to train the model. And that for testing, for example, we will add also malware files as well. So, and for feature selection, because processing 2831 or 2381 features, together, they will require computational resources. We didn't, created the new wheel like another said, for example. So what we did, we already saw some papers working on this idea, and they extracted these features. So for the comparison, for example, we used the features extracted by this research, for example. And here you see, for example, with just 25 features, for example, the training accuracy is already reaching 99%. So it was fun. We used this. And also there is very important aspect here. We have features, we have 25 feature vectors, we have data sets available, everything, but parameter optimization is also very important. For classifiers to learn well, we need to optimize them. Okay, for these 3 classifiers that we selected, lib, SVM, KNN, and RF, we optimize these features like number of trees, for example, in a random forest. By default they are 100, but you could play from 10 to 1000 just to see. And KNN, for example, from 1 to 50, we checked which parameter works well. And these are, here you see, for example, the parameters that we searched over the grid search and highest validation accuracy. So here I would tell you that we carried out this exercise only on the trend set, not on the test set, only on the trend set. Okay, and we performed cross validation for this. So here you see random forest performed perfectly well. So 99.79% means the model is well trained. So the same approach. Now training and testing is split. Here you see for the 77,000 files that were coming from benign files, we divided them into 2. So first one will be used for training. The remaining half will be used for testing, together with the malware files, which are 57,000. So here are the results. Obtained results, you see KNN 88.73 in training. Okay, because motivation of using this kind of result was to show you that the classifiers were not overfitting as well. So with KNN, with the first one neighbor, for example, we were 88.73 on the trend set and 89 on the test set. And with random forest, you see here 99.79 on the training set and on the test set 99.73. So technically speaking, if there exists a lot of difference between these 2 results, it means the classifier overfitted, but here is not the case. And here we report also 0% FPR of malware. So none of the malware was falsely accepted as the benign file, which is great. So conclusion, we have presented a malware detection approach using 1 class classification, and we have achieved 99.73 testing accuracy, percentage testing accuracy on test set of 95,000 combined, 38,000 benign and 57,000 malware files. So combining them, 95,864 files. Way forward is like, idea is to use more features, advanced features, not just, the features they already extracted or we already extracted using library. So maybe histogram features, maybe image-based features, maybe using computer vision features, maybe we will add up something. Then if you remember, we use all the classical kind of a classical. They are though state-of-the-art classifier, but still we consider them as classical. So idea is to use deep neural networks, for example, and check how these advanced classifiers, because 130,000 samples, they are sufficient enough to actually train a neural network classifier. And collaborating with industry partners and practitioners will allow us to test our approach on large scale, dynamic streams in IoT networks, also in cloud systems also. I think it would be interesting to explore these opportunities as well. If you are wondering about the references, here are the references. I'm done. Looking for the questions.
Thank you very much.
Welcome.
I have a question. I see from the presentation that for the training set, you are only using the green data set, I mean the positive ones. So, and we have seen that the model accuracy is also well, even if we consider the positive data set for the training part. So is it possible that we can consider both like positive and negative for the training part, that we can consider the label data set with both positive and the negative one?
True, that will be true for known malwares. So you already have the malwares, okay, and you are using two-class classifier, for example, to detect whether or not the file is benign or the file is a malware, right? So this binary class classification actually, and this would not hold true for unknown malwares. Here the idea is, I'm an ordinary user. I don't know, the file that I'm downloading. Let's say I downloaded, putty.exe, let's say. I want to do SSH, but I really don't know whether this file has any malware code installed in it. You got my point. So, because I don't know anything about malwares, anything about these kinds of malware that I mentioned earlier, I am just training my model on positive data only. Okay, I'm an ordinary user, right? So on this one class classification approach is very, very popular, especially where the data from the negative class is not available or has very few samples. For example, if you have to detect, fault in a machine, you will hardly have the data related to that fault, right? So this way, it plays a very, very good role, for example, to help researchers do, especially when you have the few number of samples or you don't have any data from the negative class. But here we used it intentionally. So idea was to just facilitate the end user who is not a security expert or not a technical guy, for example. That's why. I hope I answered your question.
Yeah, thank you.
I have another question actually. Did you think about reducing the anomalies to like text description and like trying to find them with LLMs? Just an idea I thought about it.
Not yet, but I saw your acknowledgement.
Yeah.
You are working on Cerex. I'm also working on Cerex. maybe in 1 or 2 months we will talk about it.
Okay.
But not yet.
Okay. Thank you.
Welcome. Yes.
I have a question.
Please.
Actually, I just had a master student graduated who was doing similar work.
Okay.
But we are trying to focus on the BODMAS.
BODMAS.
Okay. So the existing approach has different kind of features need to be extracted. One is a static feature, one is a dynamic feature.
Great. Very good question.
So if you only actually your features only depend on the benign files.
Exactly.
So maybe there's no dynamic feature which can show that's the virus. So sometimes even you have a file, PE executable file, you know it is a virus.
Yeah.
But when the negative effect didn't run through the program, so they cannot show the feature.
It's a bad
So that's our question. So sometimes you get a malware, but it stay there, hidden there, right? So it does show the negative things, but sometime later, it has been executed. They show the feature. So how do you?
Great question, I must say. It's a great question. Because, I'm telling you, the problem formulation in research is extremely important. Here, the problem formulation was to facilitate the ordinary user. But now, for example, there are companies. For example, I'm giving you an example. So there are companies, for example, Scout, or there are multiple companies working in this domain. But if there is a company, this company has to, because they have the resources, they have everything available. So one of their machine actually finds out whether or not this executable file downloaded on the entire network is a malware or is not, right? So this is the scenario now. First of all, they have to do this binary class classification to find out whether or not that malware is a malware or that file is a malware or not a malware. Here, there are different techniques. Like I told you, signature-based systems, even we can create YARA rules here. So exactly, from those YARA rules, I can detect whether or not this file is a malware or not. Now, if the file is a malware, which kind of malware? Is it a ransomware? Is it a spyware? Is it a virus or what? By going deeper into that particular file, for example, and even by looking at the instructions, copy, encryption, why this file actually is doing this. The point is, yes, I'm also working on this. Maybe you will find a paper in SEC 2025 maybe, but I'm working on this as well. Apart from categorization, so this is exactly is a problem we are working on. But then important task is categorization as well. All these files will be categorized. I hope I answered this.
That's okay.
Thank you very much.
Thank you. Thank you so much.